So now let's go back. Let's go back to the three cases that I showed you before I go through the derivation. So let's take a look at these cases again. In case one, we have a semi-infinite object, and in this case, in case one, okay. Now let's go back to the three different cases that I introduced before I went through the derivations. So let's take a look at these three cases. We have in case one, we have a semi-infinite object, and the boundary has a constant temperature given to be Ts. In case two, we have constant flux hitting at the left side of the semi-infinite object. And in case three, we have convection taking place on the left hand side of the semi-infinite object. So we actually derive everything for the case one. So the idea was we introduce a similarity variable, and this similarity variable depends on position and time in a particular way, and it doesn't depend on x and t independently. It depends on the combination of x and t in this particular form, in the form of x over t. That is going to be always the term that's going to be in the solution. So then after several calculus manipulation, we converted the heat diffusion equation into an ordinary differential equation, and this was the equation after the transformation. And the boundary conditions also need to be changed, and at x equal to 0 correspond to eta equal to 0, t equal to 0 corresponds to eta is equal to infinity. And then after you carry out the integration, you obtain this solution. And the solution is t minus ts divided by ti minus ts is equal to error function. And this is for case 1. Okay, this is for case 1. So before we proceed, I would like you to remember the definition of the error function here. Just not to memorize, but at least remember there exists an error function, and definition is given to you. This is the definition of the error function. And you can write this down as infinite series as well. So you can do Taylor expansion, so on and so forth. So if you like to see how it behaves, at x equal to 0, you have at 0, and it asymptotically approaches to 1 as x goes to large value. Okay, so this is the asymptotic approximation. So if x goes to infinity, you are going to have 1. Okay, so now let's go back to case 1. In case 1, so the solution is temperature at any point at any time is depend on function similarity variable eta, or x over square root of t in this particular way. And I also showed you how to calculate the heat flux. I simply take the derivative and evaluate it at x equal to 0. This is x equal to 0. I evaluated the derivative at x equal to 0, and this is the heat flux at x equal to 0. Again, so this is already driven in your textbook. So you don't need to drive it again unless I specifically ask you to drive it. Okay? So case 1, in most cases, if you know you have a semi-infinite object, and if you know one of the surfaces, one side of the object is at T constant temperature, the solution is here. So it's always the same. It's not going to change. In case 2, so we have a constant flux. So the second boundary condition, so when x equal to 0, we have constant flux that is equal to conductive flux. So the analysis will look similar. However, the satisfying the boundary condition will be much more trickier. So I'm not going to show you the steps, but I'm going to show you the final solution. And this is the final solution when you have a constant flux on the one side of the semi-infinite object. And again, we have ERF C here. So this is complementary error function. Okay, complementary error function. So that means 1 minus error function. Okay, so the complementary error function means 1 minus error function. So you can also have a situation where we have the convection, and convective flux is equal to conductive flux at the interface. And again, this is even more complicated to analyze. And if you go through extensive calculus steps, you will obtain the solution. Again, error function, complementary error function is 1 minus error function. And again, I'm not keeping you responsible for the derivation. You just need to know that whenever you are dealing with a semi-infinite object, you have three cases, and in the solutions for all three cases are given. So you should be able to identify these cases based on the problems that are given to you. So that is the expectation from you. And I may give you a derivation problem, but it will be simpler case as similar to the one that we just did. It's not going to be a very complicated derivation. I'm not trying to keep you responsible for calculus. I want you to learn